In this episode, we're going to make memory upgrades feel much less confusing by focusing on a few simple ideas that beginners can actually use. A lot of new learners hear terms like random access memory, RAM, dual inline memory module, DIMM, small outline dual inline memory module, SODIMM, double data rate, DDR, and error correcting code, ECC, then feel like memory is a pile of labels that all sound important but do not connect clearly. The truth is much more manageable than that. Memory support usually comes down to a few basic questions. What physically fits in this system? What generation does the system support? Does the system expect special features like ECC? And how should the modules be arranged so the computer can use them well? Once you learn to ask those questions in order, memory stops feeling like a guessing game and starts feeling like one of the easiest parts of hardware planning. Before we continue, a quick note. This audio course is part of our companion study series. The first book is a detailed study guide that explains the exam and helps you prepare for it with confidence. The second is a Kindle-only ebook with 1,000 flashcards you can use on your mobile device or Kindle for quick review. You can find both at Cyber.News in the Bare Metal Study Guide series. A good first step is to understand what our RAM actually does for the computer while it is turned on. Storage devices like solid-state drives and hard drives keep data for the long term. But our RAM is the fast working space the system uses right now while programs are open and tasks are happening. When a computer starts to feel slow because too many things are open at once, the problem is often tied to limited RAM rather than a bad processor or a failing drive. That is why memory upgrades are so common. They can make a system feel more responsive, especially when the user is doing several things at once, keeping many browser tabs open, or running programs that need room to work. For beginners, the important point is that our RAM is temporary working space, and when there is not enough of it, or when the wrong kind is installed, the system may not just feel slow. It may refuse to start properly, act unstable, or fail to recognize the new memory at all. Form factor is one of the easiest memory ideas to understand because it is mostly about shape and size. DIMM is the larger memory module style commonly used in desktop systems, while SODIMM is the smaller style commonly used in laptops and some compact systems. The reason this matters is simple. Even if two modules belong to the same general memory generation, they still may not fit into the same kind of machine because the physical size and slot layout are different. A desktop motherboard usually expects DIMM modules, and a laptop usually expects SODIMM modules. This is one of the first things a beginner should check before buying memory, because a memory module that is completely correct in generation and speed still cannot work if it is the wrong physical form. The system has to be able to accept the module in the slot before any other part of the decision even matters. The next useful lesson is that DIMM and SODIMM are not just different lengths. They are built for different kinds of systems, and the slots are shaped so you cannot casually swap one for the other. That is helpful because it prevents some mistakes, but it does not stop all of them. A beginner may still buy laptop memory for a desktop or desktop memory for a laptop because the label DDR looks familiar and the capacity sounds right. That is why support work depends on checking the whole memory picture and not just one fact on the package. You need the right form factor, the right generation, and the right system support at the same time. This also reminds beginners that compact systems can have memory limits that full-size desktops do not. A tiny machine may support only certain module sizes, certain slot counts, or only one easy-to-reach memory location. So the physical side of memory planning is always worth checking carefully before any purchase or upgrade begins. DDR generations are another place where beginners often get nervous, but the core idea is actually very simple. DDR is the broad family of memory technology, and the generation number tells you which version of that family the system uses. Common generations you may hear about include DDR3, DDR4, and DDR5. The important thing to remember is that these are not just faster versions that can all mix together. Each generation is physically and electrically different enough that the motherboard and processor must support the exact generation being installed. If a system was built for DDR4, you do not improve it by buying DDR5 and hoping it will work better. It will not work simply because it is newer. For a beginner, The safest way to think about DDR generations is this. The computer was designed for one generation or another, and you must match that design instead of assuming newer always means compatible. The reason DDR generations matter so much is that they are tied to the memory slot design, the signaling method, the expected voltage behavior, and the way the system communicates with the modules. That is why the notch in the module sits in a different position across different generations. The slot and the module are trying to stop you from making a bad match. This is a very good example of physical fit and logical support working together. Even if a module looks close to the right size, the slot shape and electrical design tell the real story. Beginners should remember that memory generations are not like storage devices where adapters sometimes help bridge one path to another. Memory is much less forgiving. If the generation does not match what the motherboard expects, the system will not simply run slower. It will usually fail to work at all, and that is why correct generation matching is one of the first memory rules every technician learns. Speed is where many people start overthinking memory, so it helps to keep the explanation plain. Within a supported DDR generation, memory can come in different speed ratings, and faster memory can improve performance in some situations. But speed only matters after you have the right generation, the right form factor, and the right system support. A beginner should not treat speed as the first thing to chase. The system may only run memory up to a certain speed, and if you install modules rated faster than that, the system often just runs them at the speed it supports instead of magically becoming more powerful. That means buying the highest speed on the shelf is not always the smartest move for an upgrade. Good support thinking begins with compatibility, then moves to capacity, and only after that does speed become the next useful detail. That order helps beginners avoid paying extra for performance the system may never actually use. Capacity planning is also important, and it is one of the most practical parts of memory support because users often notice the difference when too little memory is installed. A system with limited RAM may struggle with many open programs, heavy web browsing, virtual meetings, large files, or everyday multitasking. That does not mean more is always better with no limit. The system has a maximum supported amount of memory, and each slot may also have a maximum module size it can accept. A beginner should also remember that capacity decisions affect upgrade paths. If a laptop has 2 slots and both are already filled with smaller modules, moving to a much larger amount later may require replacing both instead of adding just one. This is why memory planning is not only about today's need. It is also about whether the upgrade leaves room for future growth or uses up the easy expansion path all at once. Mixing modules is another area where beginners can get into trouble even when nothing looks obviously wrong. Sometimes systems can operate with different memory sizes or slightly different speed ratings installed together, but that does not mean it is always the best idea. Mixed memory can cause the system to fall back to more limited behavior, reduce performance, or in some cases create stability trouble that is harder to explain to the user. The system may still boot, which makes the choice seem safe, but the result may not be as clean or predictable as using matched modules designed to work together. For beginners, the safest habit is to prefer closely matched memory whenever possible, especially when building a new setup or trying to improve performance in a noticeable way. If the modules have the same generation, similar specifications, and are intended to work as a set, the chances of a smooth result are usually better than with a random mix assembled from whatever happened to be available. ECC memory sounds more advanced than it really is, but the beginner version is easy to understand. ECC is memory designed to detect and correct certain kinds of data errors while the system is running. That makes it useful in environments where stability and data accuracy matter a lot, such as servers and some workstations. The important beginner lesson is that ECC is not just a better version of ordinary memory that every computer should use. It is a specific feature that the system has to support. The motherboard and processor need to be built with that support in mind, and many everyday consumer systems are not. So if a user hears that ECC sounds safer and assumes it should work anywhere, that assumption can lead to a failed upgrade or wasted money. As with memory generations, the right question is not whether the feature sounds good. The right question is whether this specific system was designed to use it. It also helps to understand where ECC fits in the real world so it does not feel like a random exam term. In a home laptop or a typical family desktop, ordinary non-ECC memory is usually the normal choice. In a business server, a workstation handling important workloads, or another system where reliability matters deeply over long periods, ECC may be much more important. That difference exists because the purpose of the system is different. A gaming desktop and a file server are not trying to do the same job, so they are not always built around the same memory needs. Beginners should not think of ECC as something mysterious. It is just a memory feature tied to error handling, and like all hardware features, it only matters when the system is built to use it. The right memory is always the memory that matches the machine and the task, not the one with the most impressive sounding label. Channel layout is another important memory idea, and this is where a lot of performance questions become much easier to understand. A memory channel is a path the system uses to communicate with memory, and many systems can perform better when memory is installed in a way that allows more than one channel to be used effectively. The most common beginner example is dual-channel memory. In simple terms, this usually means the system works best when matching modules are placed in the correct slots so the computer can use two memory paths in a balanced way. That is why many motherboards have slots marked or color-coded to guide correct placement. If a user installs one module in the wrong spot or uses an uneven memory setup, the computer may still work, but it may not perform as well as it could. Beginners do not need to fear channel layout. They just need to remember that memory placement matters, and the board layout is there to help them do it correctly. This is also why match pairs are so commonly recommended in everyday upgrades. If a system supports dual-channel operation, two matching modules placed in the correct slots usually create a more balanced setup than one larger module alone or two mismatched modules placed without planning. A beginner technician should think of this as teamwork between memory sticks. When the modules match and sit in the correct layout, the system often has an easier time using them efficiently. That does not mean every machine becomes unusable with one module or mixed memory, but it does mean the best result often comes from paying attention to the slot arrangement. If a user says they added memory and the system works but does not feel as improved as expected, channel layout should be part of the thinking. Capacity is important, but how that memory is arranged can also affect the final experience. When memory is wrong, the symptoms can vary from obvious failure to quiet underperformance. A system may not start at all, may restart over and over, may show less memory than was installed, or may become unstable during normal use. In other cases, the machine may boot and run but still not perform as well as expected because the memory is mixed poorly, installed in the wrong slots, or limited by the system's supported speed. This is why good memory support begins with a calm, structured check instead of a fast guess. What form factor does the machine require? What DDR generation does it support? Does it use standard memory or ECC? How many slots are present, and how are they meant to be filled for the best channel layout? Once those questions are answered, most memory confusion disappears before the new modules are ever removed from their packaging. For beginners, the best habit is to slow down and think through memory in layers. First, check physical fit, which means DIMM versus SODIMM and the right size for the system. Then check generation, because DDR3, DDR4, and DDR5 are not interchangeable. After that, check whether the system supports special features like ECC and what capacity limits apply. Finally, check the slot layout so the modules are installed in a way that helps the system use its channels correctly. This kind of step-by-step thinking removes a lot of fear because it shows that memory support is not a mystery. It is just a chain of simple checks, and if you do them in order, the right answer usually becomes very clear. The main takeaway from this lesson is that memory upgrades are easiest when you stop treating the labels as separate facts and start using them as answers to a few practical questions. DIMM and SODIMM tell you about physical form. DDR generations tell you which version of memory technology the system supports. ECC tells you whether the system expects error-checking memory for more specialized use. Channel layout tells you how to place modules so the machine can use them efficiently. Once you understand those roles, memory planning becomes much more straightforward. You stop guessing, you stop assuming newer always means better, and you start thinking like a technician who knows that the best memory choice is the one that fits physically, matches logically, and works cleanly with the system the user actually has.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.